Hey guys, welcome to this week's Friday Focus. Today we're going to work on just really nailing down definitions as it has to do with electron configurations and orbital diagrams, just to make sure we have a holistic understanding of what is going on as we're putting electrons into these orbits. So I'm just going to go and just talk about some definitions and then talk about little nuances of these definitions. You can find these definitions in your textbook, but of course the ones I'm going to use in my video are going to be in my own words. So first and foremost is the Aufbau principle. So the Aufbau principle has to do with how these electrons kind of file into their homes, into these orbitals. So electrons will fill the lowest energy level to the highest, and then each orbital or each box can hold a maximum of 2 electrons. So the analogy I like to use for Aufbau's principle, let's pretend like I'm sitting on the floor with my kids and we're reading books. We finished reading books and it's time to put the books away. They have, of course, dumped out the entire bookshelf, right? So would I pick up the first book, stand all the way up, get on my step stool, and put that book in the top shelf? Probably not. I would probably pick up the first book. I would find the nearest shelf while I'm still sitting on the ground and put a book in that bookshelf. And then I would continue to fill that bookshelf until it's full. Then I might reach to the next higher shelf and put a book there. And then, oh man, all those shelves are full, so maybe I stand up and I fill the next shelf. All of those are full. I gotta get on my step stool, pick up my book, put it on the top shelf. So I'm going to do like the path of least resistance, right? I'm going to do the laziest thing first, the lowest bookshelf, and I'm not going to fill the higher bookshelves unless I have to. So Aufbau's principle, electrons do the same thing. They will fill the lowest energy to the highest. Well, how do I know what's low in energy? How do I know what's high in energy? When we use that electron configuration, or we use the orbital diagram, that tells us or teaches us what is lower in energy. So first energy level is the lowest. Then we go to the second energy level. Now we're delineating between S and P. So S is lower, P is higher. Then we go to the third energy level, S, P. And then we see something kind of crazy happen here. It turns out that a 4s is easier to get into or lower in energy than a 3d. So think about how big and crazy those d orbitals are, right? Those are hard to get into. So they're like, I can go up to that s, which is the sphere and really easy to get into, or I can stay on this level and go to that really crazy complex d. I think I'm going to go to the s orbital. So it fills the 4s, and then 3d is the next best option. So that's Aufbau's principle. We go from the lowest energy level to the highest, and then each orbital or each box, as we see here on the screen, can hold 2 electrons. The next rule that I want to talk about is something called Pauli's exclusion rule. So this just says that 2 atoms cannot have the same set of 4 quantum numbers. They could have 4 completely different quantum numbers, all the way up to 3 identical quantum numbers. But that 4th one has to be different. There's not 2 electrons that have the same zip code, the same 4. The best way to illustrate this is just to look at an example. So I'm going to fill up, I'm going to fill up this orbital diagram and talk about some electrons. All right, we're going to talk about these last 2 electrons that I put into the 2p orbital. So if I talk about the quote-unquote address or the quantum number, actually, hang on. We're going to do this. All right, we're going to talk about these 2 electrons in the first box of the 2p orbital. If I were to do the address or the quantum numbers for these 2 electrons, so the first quantum number is 2 because they're in the second energy level. The second quantum number is the what shape they're in. So L in this case, they're in a p orbital. So when we're in a p orbital, L equals 1. So both of those are on the second energy level. Both of them are in an L-shaped orbital. The third one has to do with orientation. So let's just say this is orientation -1, 0, and +1. So both of those electrons in the first box are in the same orientation for orbitals. So they both have a -1 for the magnetic quantum number. Now this fourth quantum number is where they differ. The arrow that's facing up, that fourth quantum number is a +1/2. If we look at the arrow that's facing down, he too is in the second energy level. He's in a p orbital, so that one equals 1. He's in that -1 orientation, but his last quantum number is a -1/2 because he's spin down. So that's what the Pauli exclusion rule tells us, is that no two atoms can have the same 4 quantum numbers. They must be different in at least that fourth quantum number. And then the last one is Hund's rule. This is the one that I saw you guys struggle with the most on your lab. So I want to make sure we really hit this one. So Hund's rule says it is lower in energy if an atom has a maximum number of unpaired electrons. Again, I'm going to use the orbital diagram to illustrate this. So we're going to talk about as we're filling up this 2p orbital. So of course, the first 2 electrons go into 1s. The second 2 electrons go into 2s. So let's say I have 2 electrons that are going to go into this 2p orbital. Hund's rule tells me that they're going to go in unpaired as opposed to paired up. So unpaired means 1 in the first box, 1 in the second box. So the silly analogy that I do for this one is, let's say you're going to college and you're picking out your dorm room, right? Your RA was like, hey, you're going to be on the second floor. There's 3 rooms up there on the second floor. Go ahead and pick whatever room you want. So you walk to the first room, you peek in. Of course, each of the dorm rooms have 2 beds, right? You walk up to the first room, you peek in, and there's somebody that's getting settled in that first room. Are you going to just go ahead and hop into that room with that person? Or are you going to take yourself to the next room and see that it's empty and choose that one? You're going to go to the empty room, right? So electrons are going to do the same thing. If we're on the same energy level, filling the same shaped orbital, they will go in as unpaired first, and then when there's no other options, they'll pair up. So electron number 1 goes in the first box. Electron number 2 would go in the second. Electron number 3 would go in the third box. Now, the fourth electron doesn't have a choice. The fourth electron gets to that floor of dorms. They peek and see that there's somebody in all 3 of them, so they don't have a choice. They're going to have to partner up. So that fourth electron, it doesn't really matter which box we put it in, but that fourth electron would then pair up. And they would pair up until this was full, and then we'd go to the next energy level. Okay? So that's what Hund's rule states, is that they'll fill in unpaired first, then when there's no other option, they'll go ahead and pair up, but of course with the opposite spin. So that's our Friday focus, just really honing in on these definitions, making sure we have a complete understanding of how these electrons file into these orbitals. I hope you guys found this helpful.